In this video, we're going to introduce the next state for the player. But first, let's clean up a few things. I actually prefer to use the Gizmo's draw wire cube method because it only draws the outline, which makes it easier to see overlapping rectangles. If we take a look at the application, we can see the difference in the way the ground trigger is being displayed. We're also going to finish up our jump functionality by increasing the gravity scale if the player releases the jump button before they reach the peak of their jump height. This will have the effect of allowing the player to control how high they jump to a certain degree. If they quickly release the input, then the stronger gravity will kick in and prevent them from reaching the peak of their jump. So in the condition where the jump input was released, we will first check to see if the player's vertical velocity is still positive, and if it is, then we'll set the gravity scale to the falling gravity that we defined earlier in our settings. Let's go ahead and test our variable jump height now, even though it's missing a few things. We can now control the height of our jump, but we still don't have the correct jump animations playing, so we'll update that soon as well. We also want to implement the falling gravity when the player reaches the maximum jump height, regardless of whether they have released the jump button. This is how classic Super Mario Bros. Platforming physics works. The player falls faster than they jump upwards. This isn't realistic, but it is a mechanic that feels good for many platformers. Without this, the player can feel like they have a floaty jump. We will first check to see if the player has hit the ground in this frame. If they have, then we'll always set the gravity back to its default value. Then we'll define a minimum fall speed setting that we can use to see if the player is moving down fast enough to be considered falling. We'll compare the player's vertical speed to this setting. If this condition is true, then we'll also set the gravity to the falling value. There should actually be a negative sign in front of the min fall speed in this condition, but the difference in the gameplay is so small I didn't notice the error. Now if we run the application, our full jump functionality should be in place, except we're still missing the correct animations. We can also use our collision triggers to make sure that the player will leave the duck state if they slide off the edge of a platform after pressing duck while running. If this happens, then the ground trigger will be false and we can place the player back into the move state as they begin falling. Now let's take care of the jump animations. If we return to the player script, then we can include a series of checks that will play our jumping and falling animations at the right times. Let's include a setting that's called min jump speed to ensure that we only play the jump animation when the player is actually trying to jump and not when they are simply moving upwards slightly due to a collision resolution. If the player's vertical velocity is greater than this minimum jump speed, then we'll play the jump animation. And if the player's vertical speed is less than the negative value of the minimum fall speed, then we will play the fall animation. This is also so that they do not enter into and out of the fall animation because of collision resolution when they are supposed to be standing still on the ground. Notice that this is the correct version of the min fall speed check that I messed up when we were finishing the duck state. We have defined the minimum fall speed as positive for somewhat pedantic reasons, and as you can see, it caused me to make an error. You could easily define this value as negative if that makes more sense to you, but technically a speed is always positive because it's just the distance traveled divided by the time. The velocity is a vector that can point in the negative or positive directions. Okay, now we can test the application one more time and see that our animations are all responding correctly. Remember, we are still going to come back and fix the stickiness of the player's movement by introducing a physics material. One last loose end we're going to clean up is that we want to use a different damping depending on whether the player is moving in the air or on the ground. Now that we have a ground trigger, we can set this correctly. If we look in our move state, we can use a ternary operator to set the correct damping based on the ground trigger value when we update the velocity. We don't have to make this same change in the duck state because if the player slides off an edge, they will now be immediately transitioned out of the duck state back into the move state where this will be handled already. We will create a second smooth time setting that is called airspeed smooth time, and we will give it a larger value so that it takes longer for the airspeed to be damped. This equates to less friction, which means the player will have less inertia when jumping through the air. They will be a little bit easier to control. Now, we're finally ready to create a new script for our climb state. Remember to put this script into the player states folder like all of the rest. We'll start by inheriting the player state class, and then we'll ask Visual Studio to implement the constructor for us. We can also write the init method now. We will set the correct climb animation. We will also set the gravity to 0 in this case, because we don't want the player being dragged down the ladder by gravity when they are not climbing. And we will also set the velocity to 0, because we want the player to come to a sudden stop when they grab the ladder. Whenever we set our x velocity to 0, we also want to make sure that the damping velocity is zeroed out so that we don't have any residual velocity left over that will affect us when we begin using the damping function again. Let's make it so that when we set our velocity to 0, we also reset the velocity x damped value in our player script. We'll also check to see if the absolute value of the x velocity is being set to a number smaller than the minimum move speed. In this case, we'll also zero out the velocity. We're doing this because the damping function we're using only approaches 0. It won't reach 0 on its own, but we want our player to come to a complete stop when the velocity is damped below a certain minimum value. We'll add a public method to our player state class that simply resets the damped velocity to 0. Then we can return to the player class and make use of this method in setVelocity. Now we want to introduce a climb speed value to our settings. This speed will be a little different because we want to be able to define a horizontal speed and a vertical speed independently. So we will define the climb speed as a vector 2. We're going to have the player move significantly slower when climbing horizontally. Let's also quickly create a new instance of our climb state for the player's state dictionary. We will need to add the climb value to our player state type enum as well. Then we'll instantiate the climb state just as we've done with the others. The next thing we need to do is introduce the climb trigger collision check, because we need the player to be aware of when they are close enough to a ladder to be able to climb it. We will follow the exact same procedure that we used for the ground trigger. We will add a method called update climb triggers to the player state class that uses the overlap box function in exactly the same way that our ground trigger method does, except it will use the climbable layer mask, and we will need to define the climb bounds in the trigger info component. Let's hop over to the trigger info component and follow the pattern we set with the ground trigger. We will define a bounds object that has a public getter which updates the position of the bounds based on the player's position. We will also define a climb offset vector 3 that helps us position the bounds relative to the player's position. And then we will instantiate the bounds with the correct size in the start method. Finally, we'll make sure to reset the climb trigger. Let's also complete the reset triggers method by setting the wall triggers to null as well. We also need to remember to call update climb triggers in the update triggers method. Let's test out the application quickly to see if we are registering a collision with the ladder we have in our scene. Everything is working, but it would be nice to be able to see the climb check displayed for debugging purposes. So let's go to the player class and include another draw call that will visualize the climb bounds. Now we can run the application and see exactly where our collision check is occurring. If we switch to the scene view, then we can carefully test the collision between the climb trigger and the ladder's tiles. Now let's build out the rest of the climb state logic. The fixed update method will be simple because we are not going to dampen the velocity while the player is climbing. Instead, we'll simply set the velocity based on the move input and the climb speed value we defined earlier. Then we can perform a number of checks in the update method to manage the potential state transitions that might arise. Most importantly, let's start by calling the update triggers method. We will then check to see if we are no longer colliding with a climbable object. If this is the case, then we've fallen off the ladder, so we can set the player back into the move state. The next check is a little tricky. We want to basically check if the player has just climbed down from a ladder directly onto the ground. But the problem is that if we just check for a ground collision, that might be true right after the player starts climbing up a ladder from standing on the ground. So we also want to make sure they are actually climbing downwards when they hit the ground. And since we are comparing two non-zero float values, we should also use the approximately function to avoid floating point errors when checking equality. In this case, we'll also set the player back into the move state. Finally, if there are no state transitions to handle, then we are still climbing and we should update the player's facing value in case they turned around on the ladder. We want the animation to flip to the other side. We also need to handle some input for the climb state. We'll introduce the vertical input method so that we can check to see if we need to pause the climb animation because the player has stopped moving on the ladder. We can check to see if the vertical input has been released, and then set the animation speed to 0. Otherwise, we'll set the animation speed to 1, the default. We also want the player to be able to jump off a ladder, so we will include the jump input. If we get a jump input while climbing, then we'll set the player back into the move state and also change their vertical speed to the jump speed. This will act just like jumping from the ground. And last, we need a way to first enter into the climb state. So we will return to the move state and include an if statement that will check for this transition. If the player is entering either an up or down input while they are colliding with a climbable surface, then we will transition them into the climb state. If we run the application now, we can see that the entire climb state functionality is now working perfectly. We should be able to grab the ladder while standing on the ground or while jumping through the air. If we move off the ladder to the side, we will enter into the move state and begin falling with the appropriate gravity. All of the animations should also start and stop as expected. In the next video, we'll finally fix the sticky physics, and we'll also introduce another player state, the hang state. This will allow our player to hang from any ledge in our stage, and it will also set the foundation for an ability to climb up from a hanging position.